well, that's very interesting. But first, before we do that, we have and Max is from Snowflake, of course. But first, we have a local speaker from the Netherlands, Orson. He is a first-year PhD student at CLI. He actually made the top of Hacker News again last week, I think, because his twice even, sorry, because his sorting work caught the attention again, and Google was using it and announced to start using it, and then got more publicity. But he's going to talk about sorting, but with new stuff. So Orson, take it away.
All right, thank you. Well, there we go. Today I will present Glidesort, a new efficient in-memory adaptive stable sorting, a lot of keywords, on modern hardware. So we are stably sorting. Oh, I don't know why the arrow keys don't work. Before that, I quickly want to talk about the scope. Wait, no. Yeah, okay, there's a disorder in the slides, my bad. What is Glidesort? So it is a stable comparison sort. It can take an arbitrary comparison function and it will preserve the order of equal elements. It is a hybrid sort of mergesort, quicksort, and insertion sort. And it is robustly adaptive. So not just a corner case, not just testing for one particular input distribution. No, it's robustly adaptive to pre-sorted inputs and low cardinality inputs. And I have a reference implementation using unsafe Rust. So I quickly want to talk about my performance assumptions. I'm assuming that our data is already in memory, that we have quick random access, although we'll see that I don't actually do much random access. It's mostly linear scans. I'm assuming cheap comparisons, like comparing integers or comparing subsets of a struct, like cheap comparisons and cheap moves. So if you're sorting objects that are like a kilobyte large or even larger, you're probably better off with another algorithm. So it's a traditional system sort. You might wonder, stable quicksort? I thought that stable quicksort wasn't a thing. And in fact, if you look up on Wikipedia, quicksort, all it will tell you is that it's in place, that it uses element exchanges. And in fact, it will straight up tell you that all efficient implementations of quicksort are unstable. That's not necessary at all. You can use extra memory to make quicksort stable. And for some reason, standard stable sort uses extra memory and everyone's fine with that. But as soon as stable quicksort uses extra memory, everyone loses their minds. That's an impossibility, apparently. I also want to quickly talk about adaptive sorting. So I already said it's robustly adaptive to low cardinality and ascending inputs. And that essentially means that if your input already contains pre-sorted sequences, or if your input consists of many elements that are actually compare mostly equal, we can take advantage of that. There are two main schools of divide and conquer sorts. There's the merge school of divide and conquer sorts, so mergesort, Timsort, Powersort, and they're all fundamentally bottom up. So they start with the smallest arrays and they keep merging into larger and larger arrays until you're done sorting. And these are very good at being adaptive to pre-sorted runs because you can just take the pre-sorted runs in your input and immediately use those in your merging. The other school is partitioning, which is like quicksort or sample sort or radix sort, where you're partitioning your data into several buckets. And you can do this to be adaptive to low cardinality inputs. If you notice that your bucket is completely equal, then you don't need to recurse any further on that. So to zoom in a bit, low cardinality inputs doesn't necessarily mean that there's very few different kinds of elements in your data set. It just means that whatever you're comparing on has very few elements. So even though your customers might be very varied, there might only be like 20 cities, or there might only be 5 car brands in your data set, but many cars. I'm mainly going to be focused on adaptive quicksort for low cardinality inputs, whereas quicksort originally was made in the 1960s. And then Dijkstra posited a problem later where we do have many equal elements, and he used the Dutch national flag, so red, white, and blue balls, and you want to sort them in order. And it wasn't really until my work in 2015 on pattern defeating Quicksort that we found a method to use Quicksort in a way that handles equal elements very efficiently without using three-way comparisons. So I have an entire talk on pdqsort, so I won't go into too much detail here, but I essentially have a little heuristic that tells me whether to use a partition that puts equal elements on the left or a partition that uses equal elements on the right. And by recursing with this efficiently, you essentially form a three-way comparison without using actually three-way comparisons, because in most programming languages, a three-way comparison ends up being just two comparisons. In adaptive mergesort, it's a very simple idea. You just take the runs existing in the input. The problem is, how do you make sure that your merges don't become very unbalanced if the the runs in the input are very unbalanced? And you need to store the information of your runs. So the main known algorithm for this is Timsort, although Knut already described natural merge sorts earlier, natural meaning taking advantage of input runs. And I am very interested in the work by Powersort, and it's Powersort that I based Glidesort on, because they have a very interesting technique. The main loop of Powersort looks like this, where we create a new run, which can be existing in the data, or we just use insertion sort to make a run. We compute that run's power, and then as long as the power on the stack is larger than the power of the new run, we merge and continue. So the power of a run is quite involved. I don't have enough time to talk about it in detail, but the main idea of it is that you look at the interval between the midpoints of your current run and your previous run, and you look at how many bisections of the original array it would take to end up slicing somewhere in that interval. And I found a very efficient way of computing this that doesn't require integer divisions all the time. You just do one integer division, and from that point on, it's just 2 multiplies, 2 additions, XOR, and they count leading zeros, which is very efficient on most processors. But a problem emerges. We saw that being adaptive to pre-sorted runs, all these algorithms are fundamentally bottom-up. You need to start at the small things and work your way up. Whereas the things that are adaptive to low cardinality inputs are fundamentally top-down. You're constantly partitioning out. So how do we solve this? We glide. So a soaring bird only flaps its wings when necessary. And in a similar way, Glidesort only sorts when necessary. And we do that by extending our idea of a run to a logical run, where it can be unsorted, sorted, or the concatenation of 2 sorted ranges. As I already mentioned before, that create run can take advantage of existing runs in the input in Powersort. And in Powersort, create run forces to always make a run. It always forces to make a run. In Glidesort, we don't do that. We don't insertion sort immediately. If we try to make an ascending run and it doesn't exist in the input data, we just return the unsorted run. And that's it. We'd leave it unsorted. This leads to a more complicated merge algorithm, because we're actually doing a logical merge. We replace the merge operation in Powersort with a logical merge. This looks very complicated, but essentially we're saying, if 2 unsorted runs still fit in their scratch space, we just concatenate them. If not, we quicksort them and then concatenate them. If we have 2 sorted runs, we concatenate them. This is all just bookkeeping, it's free. If we have an unsorted run and a sorted run, we quicksort the one that's unsorted and then recurse as a logical merge. And finally, if we do have 2 sorted runs or more sorted runs, we do an actual physical merge, which can be a triple merge or a quad merge. So the main loop of Glidesort is an extension of Powersort, although you could do with other natural merge sorts. It does not eagerly sort small runs. It keeps them unsorted. It defers physically merging runs and sorting runs as long as possible. And by doing this, it transforms the problem of sorting into a sequence of quicksort calls and balanced triple and quad merges. And this is adaptive to both pre-sorted runs and low cardinality inputs, although the low cardinality low-cardinality inputs do need a sufficient buffer size. So why triple and quad merges? There's three main reasons. We can use ping-pong merging, bidirectional merging, and parallel merging. Ping-pong merging is a replacement of the traditional merge where you copy out the smaller of the two arrays and then merge back into the gap. Instead, we can merge both on the way out and on the way in. So if we have four, in this case, a quad merge, if we have four sorted runs, we can merge these two into the scratch space, these two into the scratch space, and merge on the way back. Bidirectional merging we can use if the destination and source array of a merge are disjoint. Then we can merge from both ends. Instead of starting on one end on both arrays and scanning, we can start at both ends. Why? Why is this important? I don't know, the slides just keep skipping for some reason. So why? It's because our modern processors are superscalar, they're out of order, and they're deeply pipelined. We get rid of the deeply pipelined issue by using branchless merging. This is already a known technique. But one of the things that isn't addressed in the current merging algorithms, the state of the art, is the superscalar and the out of order part. Because if we analyze the dependency of a branchless merge, what we notice is that every operation essentially is needed immediately. So you can't really use instruction level parallelism. You can't really hide latencies. So that's my main takeaway from this talk. That's relevant, not just to sorting, but to everything. And that's to interleave independent branchless loops. We do the same thing with parallel merging. If we have two independent merges, we can do them in parallel, but we don't use threads. We just interleave the loops, taking advantage of instruction level parallelism. So I have And finally, we create even more parallelism when possible by doing a quick binary search and finding the crossover point where we can swap two equal size buffers in the middle to create two smaller cases of merging. And if our merge is out of place, so we're merging into some other location, this swap is free because all you do is reassign the source buffers. Finally, this also forms the fallback operation when the buffer size in Glidesort is not large enough to hold the entire array. We can use this to create smaller instances to recurse on. So I have an example of what that ends up looking like. So you can see that it is actually merging in multiple locations at once by interleaved loops. I have, one second. Slideshow. Did the screen share end entirely or? No, we're back. Okay, we're good. Okay, yeah, we've seen this one. Can we skip Google Slides, please? Thank you. All right, I apply a similar logic to stable partitioning. So that's partitioning into some scratch space. I have two scans that move from either side, and the stuff that they both put their data into disjoint regions of memory, depending on whether it's less or greater. Again, I don't have the time to fully explain this. It does make Quicksort quite a bit more complicated, and you have a lot of cases down on the recursion, but it can be done. And it does mean that you can turn stable Quicksort into interleaved loops that are independent. So I have an example again, where we can see that Quicksort is being used and being adaptive to low cardinality input at the same time as we are adaptive to pre-sorted runs in the input. So here you can see that it just straight up skips the whole equal element bits. And again, it uses interleave loops to merge. All right, Google Slides does not like videos. So I will talk a bit about actual numbers. This is my experimental setup. It's a 2021 MacBook Pro. I use the latest version of Rust, and I don't know if it's the latest version of Clang, but it's pretty recent. And we have roughly 12 megabytes of cache. Oops. So these are the actual numbers that you end up with. And Glidesort is very fast. It is not only 4 times faster than STD stable sort for random data, so no input distributions being used here. It is also just the fastest for any data, for any sorting algorithm, whether it is stable or not. If we limit Glidesort to a buffer of roughly 1K elements, we can see that it's still faster than STD stable sort by a factor of 2. And well, it's no longer the fastest algorithm overall. It only uses a constant amount of memory. So you can do very efficient stable sorting in place almost. And if we look at the case where we can actually observe our stable sort and have a low cardinality input by masking out just the bottom 8 bits of each integer, we can see that Glidesort speeds up even more and starts beating the Rust stable sort and the STD stable sort immensely. And I'm very excited about that. I hope you are excited about that. If you want to use it, you'll be able to soon. I'm still working on cleaning up the code and really doing some insane sanity stress tests to make sure there's no bugs. In particular, exception safety is not yet in the current implementation, where I'm currently assuming that the comparison operator can't panic, but in theory it could panic and you have to do a lot of cleanup. But soon I will release it under a permissive license. And that was my talk. Thanks, you.
Thanks, Orson. So that is for the interesting talks for